All right, the Bhagavatam Bang. I don't know. That's kind of a lame title, in my opinion, but that's what we're rolling with today, subject to further revision. So this is about the Big Bang cosmology. So the Big Bang is, I think, really one of the two, I think, along with evolution, of the main reigning scientific theories of our time. And even people who don't adhere necessarily to a scientific, or at least explicitly adhere to a scientific paradigm of life, people who are worldview is much more faith-based, regardless of what that faith may be. Still we live in a world that's ruled by science, that's governed by science, even if people are scientifically illiterate. If the lay people are scientifically illiterate, the underlying mechanisms that make our society run are all very much based on science and very much based on scientific methodology in action on a daily basis. Otherwise, things don't work, or things revert to a more dictatorial, monarchical, or hierarchical power structure as far as the reigning power structures in society. Anyway, I digress a little bit. The Big Bang and evolution are certainly the two biggest scientific theories out there, and the two that I think are commented upon most by devotees, by devotional audience, when wanting to somehow establish the existence of a God. The tendency is to want to try to debunk the Big Bang theory, or to want to find threads within the Big Bang theory that can be pulled on to lead an audience or to lead a hearer into a more theistic or into a more faith-based view of the universe. And that is all fine and good. That is all fine and good. As with any scientific theory, there are certainly threads that can be pulled on where the theory may start to unravel, or where more questions may arise than answers may be available. However, I think within the devotional audience, and if there are people who are listening to this on my Facebook page or somebody's Facebook page that are not part of the devotional audience, I do apologize for using some jargon and some lingo, but the assumption is that most of the people listening to this are devotees. When approaching our mission with this mentality, it's important to understand what the facts of the argument we're arguing about are before we start to argue against them. Otherwise, we really look quite foolish. And so the first part of this presentation is just going to explain what those facts are. What does the Big Bang Theory really say about the universe, and why does it say that? So what are the, well, we'll just get right into it here. So the Big Bang Theory, or as it's called in modern physics, the lambda cold dark model, or lambda CDM, that A was supposed to be a Greek letter, lambda. This is called the Big Bang model. And the Big Bang model, or the Big Bang Theory, I should say, is a theory that explains 4 very large scale, ubiquitous observations we make about the universe that we live in. And I put these 4 on the screen right now, and I'm going to go through each of them in a little bit of detail while explaining the timeline of the Big Bang and how we got to where we are today, quite literally, in the universe, in time and place. So the first is the existence and the structure of the cosmic microwave background radiation, which is a cosmological footprint that was detected in the 1960s. The other one is the large scale, another one I should say, is the large scale structure and the distribution of galaxies. So anywhere we point a telescope in the universe has 2 fundamental properties. It is number one, isotropic, which means it is structured the same in all directions. There's no observable statistical anomalies in the underlying structure of the universe. And it is also heterogeneous, which means that the matter in the universe is distributed relatively evenly, or at least there's no major statistical anomalies in the manner in which we perceive matter in the universe. The third one is the abundance of elements in the universe, and we detect the abundance of elements in the universe through the fingerprint of stars, or the light fingerprint of stars, I would say, and I'll get into that in some detail. And finally, and perhaps what is the most well-known piece of evidence that would support the Big Bang Theory, is the accelerated rate of expansion of distant objects away from us, otherwise known as the redshift. which was discovered by Edwin Hubble back in the 1920s, I believe, and for which he got a telescope named after him. So that's pretty cool. Very quickly, I'm going to go through the timeline of the Big Bang. The Big Bang timeline starts up here at the top of the page, where in the very first instances of the universe, there was a rapid expansion of space. And when I say the very first instances, good morning. When I say the very first instances, we're going to have a visitor on the camera. There she goes. We're talking about 10 to the negative 42 to 10 to the negative 32 seconds. So that's a decimal point with 41 zeros and a 1 at the end of it, seconds. The universe rapidly expanded. And this length of time is what's known as the Planck time, or the Planck moment. And that is the earliest in which we can detect the separation of gravity out of a unified quantum field. So before this Planck moment, or this Planck era, there was what is known as a singularity, which is that all of the mass and energy that was in the universe was in an infinitesimally small and infinitely dense point of space. And at that moment, and this is sort of, I think, common knowledge, I would say, amongst the devotional crowd and amongst the secular crowd, that at that moment of the singularity, the laws that we know govern quantum mechanics, which is the behavior of matter on infinitesimal spaces or distance scales, sort of contradicts the laws of gravitation, which is what governs the behavior of matter on cosmological scales. And so the amount of time after the Big Bang in which those two things can be separated from each other and have some tangible reality to each other without causing a problem is this Planck moment, which is 10 to the negative 42 seconds. And this is accompanied by a rapid expansion of space and a rapid cooling of the universe. So as things expand, they cool down, which is why, like, when you spray your laptop with a can of compressed air, the can gets cold. It's because the air in it is expanding. So as things expand, they cool down. And so during this time, the universe cooled down from about 10 to the 27 Kelvin. That's a 1 with 27 zeros after it, Kelvin. 0 degrees Kelvin is 273.15 degrees Celsius. So at these temperature scales, the difference between Kelvin and Celsius is not terribly relevant. And as things cool down, they condense. So, for example, as steam cools down, it condenses into liquid water, and so on and so forth. So as the universe expanded and cooled down, matter began to condense into what we call baryonic matter, or matter that has some mass to it, or has some tangible, tactile function to it. And so this began first with the condensation of matter and antimatter particles. And then these matter and antimatter particles, through a series of recombinations, and this is actually called the recombination era, eventually began to form hydrogen and helium nuclei. And as this happened, the universe began to cool further and further and further, and so on and so forth. This led to, this is where the cosmic background radiation originated. So as these subatomic particles were colliding with each other and recombining, they were emitting gamma radiation. And as that gamma radiation is spread out over time and space across the universe, its wavelengths has stretched to become no longer gamma rays, which have very short wavelengths, but microwaves, which have incredibly long wavelengths. This led to a period of time known as the Dark Ages. So after all these subatomic particles condensed and recombined into neutral atoms, neutral hydrogen and helium atoms, the universe was dark. And there was two reasons for this. One is that whatever residual radiation was left over from the recombination was immediately absorbed by the energy density in the universe. So there was so much energy density in the universe that all of the photons emitted from the radiation were immediately recaptured or dispersed. So nothing was really able to shine. The other reason is that because the atoms in the universe at that time were neutral, they weren't emitting any new radiation. And so there was a period of time known as the Dark Ages, which began after the formation of the initial elements, but before the next period, which is the reionization of the universe. And that is when the first stars appeared in the universe. At least that's what people thought until a couple months ago, when the James Webb Telescope discovered enormous galaxies at a distance from us that would represent a much younger universe than we originally thought galaxies like that would form. Anyway, that brings us to the reionization. So there are neutral hydrogen and helium atoms, but under the attraction force of gravity, they start to become attracted to each other. And if enough of them become attracted to each other, that creates enough heat of fusion to actually ignite a nuclear reaction. And now that would reionize all of these atoms, and it would eventually cause stars to shine. And that's where the young universe that we can perceive now really began. And the evolution of stars over time leads to the formation of modern present-day galaxies, which is kind of the last step we see here. And so these are the general time. This is the general timeline of the Big Bang. Obviously, I'm leaving out a tremendous amount of detail. There is a tremendous amount more detail to be gone into here. So if people think that scientists are just kind of like making this stuff up or whatever, they are definitely not. I'll get more into that in a moment. So basically what we see is a picture of the universe rapidly expanding. As it expands, it cools down. As it cools down, matter condenses and recombines into progressively more evolved forms of matter until we have what we see today as modern galaxies. I'm not going to go too much into this, but there will be a math test at the end of the class. So if you understand any of that math, you will pass the test. The rest of us are just going to go get some bagels, cream cheese because it's Sunday. Anyway, these are the four fundamental forces of the universe. So as a consequence of the universe rapidly expanding out of the singularity, these four forces uncoupled from each other. And these four forces form the basis of the standard model of the universe today. And very quickly, they are gravity, which is the force of attraction between mass-bearing objects. There's electromagnetism, which is exactly what it sounds like, electricity and magnetism. And we perceive this most directly throughout the cosmos in the form of light. Not just visible light, which is the Roy G. Biv spectrum, but everything from gamma rays to radio waves along the spectrum. And I have a slide that shows that too. There's the strong nuclear force, which holds protons and neutrons together in the nuclei of atoms. And then there's the weak nuclear force, which governs the charge of protons and neutrons in the nucleus of an atom. So if a quark flips in a neutron, it can become a proton, or if a quark flips in a proton, it can become a neutron. And this is all governed by the weak nuclear force. And that's what also leads to radioactive decay. Just to revisit the initial recombination, Prabhupada spoke about anti-material particles in his Easy Journeys to Other Planets, and he knowingly was using that as it's called a MacGuffin in literary terms. A MacGuffin is something you use to open up a whole new doorway. But this is what matter and antimatter really are. So in matter, we have positively charged protons in the nucleus of an atom that are being orbited by negatively charged electrons in a cloud, a statistical cloud, basically, around the nucleus. Antimatter is the same thing, but the charges of the particles are flipped. So instead of having a negatively charged electron, we have a positively charged positron. And instead of having a positively charged proton, I'm pointing at my computer screen, like you can see what I'm pointing at. Here we go. Instead of having a positively charged proton, we have a negatively charged antiproton. And when these two things collide with each other, they emit gamma radiation. And so that's what was going on, according to the theory, at the beginning of the universe. And that's why we see the cosmic microwave background now, because what was initially emitted billions of years ago as high intensity gamma radiation has dispersed and diffused throughout the universe over time and is now microwaves. And if we wait another couple billion years, they will be radio waves, and so on and so forth. The collisions of protons and antiprotons. So that's the collision. Oh, I got ahead of myself. That's the collisions of electrons and positrons to produce gamma radiation, which is what we perceive now as the cosmic microwave background. The collision of protons and antiprotons, which, remember, we're condensing out of this very rapidly cooling and expanding universe. These collisions between protons and antiprotons produce a variety of other subatomic particles, more electrons, antineutrinos, which is an antimatter neutron, and then a bunch of quarks. The quarks can then recombine to produce protons and neutrons. And so what the result of this is a gradually accumulating reservoir of matter over antimatter. There we go. So that was just a little bit about recombination. I want to talk a little bit about electromagnetic radiation right now, which relates both to the redshift as well as the cosmic microwave background. So this is an image that shows the frequencies of electromagnetic radiation. So this is the wavelength. That's the distance. If I have a sine wave, the wavelength is the distance between two peaks or valleys of the wave, or any two congruent points along the wave. And a radio wave has a wavelength on the order of magnitude of 1,000 meters or a kilometer. Gamma rays on the other end of the spectrum have very short wavelengths on the order of 10 to the negative 12. So this is like a, what is that, a nanometer? No, that is a picometer. 10 to the negative 12 is a trillionth of a meter. And so the shorter the wavelength, the higher the frequency. The higher the frequency, the more dangerous the radiation is. So things, X-rays above here, and even some ultraviolet wave rays, this is called the ionizing radiation. This is the stuff that will give you cancer. This stuff down here, this is not ionizing radiation. So people who think standing near your microwave is going to give you cancer, that's not actually true. That's a misnomer. Anyway, and so the wavelengths, this is the visible light spectrum that we can see here, the Roy G. Biv. And the wavelength of the type of radiation is also equivalent to the temperature. So the microwaves now that we see in outer space are akin to the temperature that we see in outer space right now, which is extremely cold. But when they were first emitted as gamma radiation, the universe was extremely hot. So in the light, we also see a temperature record of the universe. And so this is about the cosmic microwave background now. So when these electrons and positrons collided en masse, we're talking all of the ones that were in the universe, they emitted this gamma radiation. But as the universe continued to expand and these waves lost their energy, we perceive them now as microwaves, and we perceive this everywhere we look in the universe. Maybe I'll get into some more detail about that now in a moment. So we have the cosmic microwave background. I want to skip ahead to the abundance of elements in the universe, and I also want to fast forward a bit in time to the reionization and the birth of stars and galaxies. I know this looks very complicated. This is nuclear chemistry here. And so at the end of the recombination, we had neutral hydrogen atoms, which is what we see up here. And neutral hydrogen atoms, this is a hydrogen with one proton and one electron. If I take two of those, so this is the atomic mass up here, which is the sum of the protons and neutrons. And so the hydrogen 1, it's a protein isotope of hydrogen. It means it has one proton and one neutron. One proton and one electron. If I take these two, if I fuse them together, I will get hydrogen 2. And this will emit some subatomic particles. I mentioned the weak nuclear force. So you think that, let me make sure I get this right. So you'd think that this, there we go. So you'd think this now has two protons, but one of the protons undergoes a change in its weak nuclear force and it becomes a neutron. So now I have a hydrogen 2 atom, which has a proton, a neutron, and an electron, like this. And if I take two of those together and fuse them together, I will get a helium isotope, helium 3. And if I take one more protein ion, that's this one up here, and fuse it with the helium 3, I will get helium 4, which is the first noble gas on the periodic table of elements. This is an extremely stable atom. And so these started to form towards the end of the recombination at the beginning of the Dark Ages. And this is what's called a neutral atom. And there was also a lot of neutral hydrogen 2 left over in the universe. But this helium 4 is really the first stable atom that formed. And then if I look over here on the left side of the diagram, I see what's called the proton-proton chain. If I fuse two helium atoms together, I can get a beryllium atom. And if I add one more helium atom to this, I can get a carbon atom. And in this way, if I look on the periodic tables through the process of interstellar nuclear fusion, so this is all going on in the furnace of stars, I can get all of these elements up to nickel here in iron. And this is why terrestrial planets have a stable iron nickel core. This here in the middle, this is the CNO cycle. This is another chemical pathway or nuclear chemical pathway by which hydrogen and helium can fuse together to get heavier and heavier isotopes of elements all the way up the line here to about iron and nickel. This requires a little bit more mass in the beginning, so larger stars can enter into the CNO cycle. And the carbon, the nitrogen, and the oxygen in this, they act as a catalyst to make the fusion go a lot faster than it would if it was just doing the proton-proton chain, which is shown here. So this is how the original stars in the universe started to fuse heavier and heavier elements. And we know that if stars get big enough, they can explode in a supernova, and that generates enough energy to fuse all of these other heavier elements here on the periodic table. So the Big Bang Theory, in addition to explaining the cosmic microwave background, also explains the origin of chemical elements that we see throughout the universe. And this is how we observe this. I'll go back to that previous slide in a minute. So most of the mass in the universe is hydrogen. This is the log of the abundance. So there's, about 10 to the 9 is helium, about 10 to the 10.5, 10, 11 is hydrogen. And as we go down the list, this all becomes progressively less and less and less. And so about 75% of the mass in the universe that we observe is hydrogen. About 25% of the mass that we observe in the universe is helium. And the rest of it, which is basically zero, is all this other stuff. So the Big Bang timeline also explains this other seemingly unrelated piece of evidence regarding the abundance of elements in the universe. And I just want to come back to this Hertzsprung-Russell diagram. I showed this in the first talk that we did. This is a diagram of observations of millions upon millions of stars in the universe and their light spectra. So by observing the spectra that these stars are emitted, we can see where along this process the star is. There's a frequency of light emitted by each one of these nuclear reactions. And by plotting that, we get this image, or we get this model of the life cycle of stars. I mean, I won't go into great detail about this, but this is how we know about what the abundance of the masses in the universe are. For example, we know from gravity studies that our solar system, 99% of the mass is in the sun. And so even if these stars have other planets in orbit around them, most of the mass is in the star, and we can tell what the star is made out of by looking at its light signature. Here's just some eye candy. This is the solar nebula. So this is where these stars, so I mentioned that these atoms come together under the force of gravity, and when enough gravity accumulates enough atoms, it ignites into stars. And that's what this looks like in outer space. This is the Eagle Nebula. This is a very famous picture taken by the Hubble Space Telescope called the Pillars of Creation. This is the Eagle Nebula in visible light. This is the Eagle Nebula in infrared light. And these were two of the most amazing pictures in all of astronomy until about a year ago, when the James Webb Telescope took these pictures of that same object. This is its near infrared camera. So the James Webb Telescope has special capabilities in the near and medium infrared ranges. And that's what we see here, near infrared light, on the viewer's left, and medium range infrared light.
What is that we're looking at? Actually?
This is a solar or stellar nebula, which is hot gases that are condensing under the force of gravity. But there's so much matter in there that under the force of gravity, they condense, and it creates enough heat for stellar fusion to ignite. So these are stars being born out of a cloud of hot intergalactic gas. And so we observe this, like here, I showed here. This is visible light. You can see the stars being born. If you turn on the infrared camera, which is before the stars really ignite into visible light fusion, in the infrared spectrum, we can see a lot more stars being born in here. So that's why being able to perceive, and this also goes back to what I was talking about with the limited senses and the asymptotes of knowledge, that we can expand our ability to perceive things with technology. My eyes can only see in the visible light spectrum, but I can develop technology by which I can see in further ranges. All right, then the next thing, kind of the last thing I want to talk about here before talking about the Bhagavatam and what this has to do with the Bhagavatam is the redshift, which is perhaps the most well-known evidence of the Big Bang. Before I get into that, I want to circle back and talk about a thing called Olber's paradox, which led directly to the discovery or the coining of the term the Big Bang. So Olber's paradox was a philosophical idea that was batted around at the end of the 19th century and the beginning of the 20th century, when people were trying to put parameters around the scope of the universe. The reigning idea was that the universe is in a steady state. It has always existed as we see it existing right now. But this led to what is called the Olber's paradox, which is the idea that if the universe is both infinite and eternal, it would follow to reason that at any line of sight I can look out into the sky, my line of sight will eventually hit a star. And if the universe is also eternal, there would be an infinite amount of time for the light from that star to reach my eyes. And so therefore, the entire night sky would be lit up with starlight all the time. Because everywhere I look, there would be a star whose light would be visible to me. And that's not what we observe. So this is called Olber's paradox, O-L-B-E-R. Olber was a guy. I don't know anything about him other than he had a paradox named after him. And so when Einstein came around and all of his contemporaries, Hubble, the quantum mechanics guys, they were aware of this and they were discussing this idea. And it started to fall. And so Einstein himself, who was a main proponent of the steady state theory, was also having some doubts in this. And the idea started to arise that the universe had to have had a beginning, right? And meanwhile, while we started to wrap our heads around the idea that the universe had a beginning, Edwin Hubble discovered that distant objects in the night sky, the light coming to us from them was all shifted to the red end of the spectrum. And that led to the, I think these stars are a little out of order. Yeah, that led to the idea that these things are all moving away from us. This is something called the Doppler effect. So if you have a stationary source emitting a wave, you're going to perceive the wavelength of that wave the same wherever you stand around it. But if that source is moving, if it's moving towards you, the waves that are coming towards you will be compressed and they will be shifted towards the blue end of the spectrum. And if the source of the wave is moving away from you relative to where you are, you can also be moving away from the source. The waves will be stretched and will be shifted to the red end of the spectrum. We experience this anytime a siren drives by us on the road. As it's coming towards us, the siren is high pitched. As soon as it passes us, the siren becomes low pitched. It's because as it's moving away from us, its waves get stretched out. And as it's moving towards us, its waves get compressed. The same is true with electromagnetic radiation. So Hubble looked up into the sky and he saw that all of the distant objects in the sky were moving away from us. And he hypothesized that that must mean the universe is expanding. And then meanwhile, his, I don't know if he was his buddy, but a contemporary of his, George Lemaitre, who was a Catholic priest working in Belgium, he thought that if you rewind that tape of the universe expanding all the way back to a single point, you would eventually come back to a single point. And then if you press play again, it would expand like this. And they called it the Big Bang. It was originally a bit of a pejorative term. They thought it's not some big bang like this guy's proposing. But it turns out it might have been some big bang like this guy's proposing. And so we see this in the red shift of light. This is an image, well, this is one of the most famous images in all of modern science, I would say. This is the original Hubble deep field image. And so they named a telescope after Hubble, and they thought, let's look into deep space in honor of Edwin Hubble. And they put the telescope up into space, and it didn't work right. There was something wrong with one of the mirrors. And this was a public relations disaster. This was a PR nightmare in the news. Like, they spent all this money on this telescope. It was supposed to be this big technological revolutionary thing, and the thing doesn't even work right. What's going on here?
What year was that?
Well, that was, I think, in 1993. It was during the Clinton administration. I don't know the exact year, but it was during the Clinton administration. And they discussed all these workarounds. I thought, well, maybe we should go up there and bring it back down and fix it, which would have been something they'd never done before, to take something like bring a satellite back down and fix it. They thought, let's build another one. That wasn't a great idea. Eventually, they had the idea that they couldn't mechanically fix it, but they could write a computer workaround. Like, they were able to calculate what the problem with the mirror was, and they were able to write a computer program that would correct it on the image that we saw. And so they did a spacewalk, they repaired it, and they wanted to test the telescope to see if it worked right now. And so they pointed it to a very narrow area of the night sky where previously they thought that nothing existed. They found the darkest spot of night sky, basically, that they could find. They pointed the telescope at it and they took this picture, which is the Hubble Deep Field. So everything you see in this picture, except for some of the really bright things in the foreground here, like this, everything you see in this picture is a galaxy. And every one of these galaxies has trillions of stars. And there's galaxies that they detected in here that you can't see. I think they counted 1 million galaxies in this picture. And this is like a fraction of an arc second of the night sky. And so the ones that are circled here, 11.9, 8.8, so on and so forth, these are the red shifts of these galaxies. And so they zoomed in up here on them. And the redshift has become a proxy for how far away something is from us. So we know that we know how far we can tell from the light of these stars what the spectrum should be, and we can see how far it's been moved to the red end of the spectrum. And by combining those pieces of information, we can develop a metric that tells us how far away this thing is from us in megaparsecs or in light years. Megaparsecs is much larger than light year. That does bring me back to these slides that I had here about how do we know generally how far things away are from us, which also raises the question, like, why does the Bhagavatam say the universe is so small? We can see things using parallax, which is, I'll get into parallax in a minute. We can see things into parallax here out to a few tens of thousands of light years. So a light year is trillions of kilometers. And using parallax, which is just a geometric distance. So if we're in a relatively fixed position, or I'm sorry, if there's something out in the distance that is in a relatively fixed position, and we are moving from side to side around it. So in the summertime, we're on this side of the sun. In the wintertime, we're on this side of the sun. The fixed star in the distance will appear to move from left to right. And by knowing the distance or the diameter of this ellipse, and by knowing the distance that the star is moving from my point of view, we can calculate how far away the star is. And that's called parallax. And we can use parallax to measure things that are much larger than the 4 billion miles that's described in the Bhagavatam. So that's a fun play. But as we get further away from where we are, things start to get more and more speculative. But we use the redshift of light to measure how things are far away from us. I don't want to go into that too much because we're running out of time. Anyway, modern news. So this whole PowerPoint is probably going to need an update in a year, because the James Webb Space Telescope just a few weeks ago took this picture, which shows here at much larger redshifts than were in the previous image. So these redshifts are 11.9. And when Hubble took that picture, that was like, oh my God, that thing is so far away from us. Holy schmoly. These things are much even further away from us, which means that they're actually found in the area where previously we thought we would be observing the galactic dark ages. So that puts a major wrinkle in the Big Bang Theory. So now we found some evidence here that actually contradicts our understanding of the theory. So if we go back to the beginning of the presentation, we saw that there was an area of time where there was nothing shining in the universe. But the James Webb Space Telescope, literally just a few weeks ago, has found super large galaxies in that time period. So that changes our understanding of the model. Just a couple more picture of eye candies. The last piece of evidence talks about the isotropic and homogeneous nature of the universe. So again, isotropic means that there are no statistical anomalies in the structure of the universe, that it's broadly the same everywhere you look. There's no up, down, left, right, east, west, north, south. It's all the same everywhere you look. And from any point you're standing in, the universe is expanding away from you. This is an artistic image of our local supercluster of galaxies called Laniakea. And it shows kind of what are called these galactic filaments, where these long lines of light tracing out through the universe are interconnected webs of galaxies swimming in a pool of this dark matter here. So again, artistic representation. Here's another one. This is called the Both model, and it shows how these galaxies form these large-scale superstructures throughout the universe. Is more intergalactic, what is it called? Cosmic filaments. And you can see the order of magnitude here. The scale here is 125 megaparsecs. So this is gigantic. This is many, 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 many hundreds and thousands and even millions of light years across. And so this is detected with gravity largely and light, and is put into these computer simulations until we get our picture of the universe being, this is the universe down here, this is us, this is a long way to go to here. We get a picture of the universe being isotropic and homogeneous. That means the matter is distributed evenly throughout the universe, and the scale, the structure of the universe is pretty much the same everywhere we look. All right, so that's the Big Bang Theory. What does that have to do with the Srimad Bhagavatam? Well, we love to point out, well, what existed before the Big Bang, right? That's always the question. It couldn't have just been the Big Bang, there had to have been something Big Bang. And you know what? That was exactly what Narada asked Lord Brahma here. If you've been following around the Bhagavatam classes at New Ramanreti the last few weeks, we've been reading this section of the Bhagavatam where Narada, so in the beginning of the second canto of the Bhagavatam, Sukadeva Goswami begins talking to King Parikshit in earnest. The first canto is like an introduction of the whole thing. Sukadeva Goswami makes an appearance at the very end of the first canto. The conversation between Parikshit and Sukadeva begins really in the second canto. And one of the main things they're talking about throughout the second canto are the scheduled incarnations of Krishna in this universe. And one of the incarnations of Krishna that they talk about is the universal form of Krishna. And Parikshit inquires a little bit further into the Lord's creative energies, as he calls them. He wants to hear about the Lord's creative energies. And so Sukadeva Goswami narrates the story of this conversation between Brahma and Narada, his son, Brahma's son, where Narada also asked this question that every skeptical person about the Big Bang asked. Yeah, but what was there? There had to have been something there before the Big Bang. And Brahma said, yeah, you're absolutely right. There was something there before the Big Bang. And he talked about the story of his birth into darkness out of the navel of Vishnu. And he explains this whole process of creation of the material world. So it's important here to make the distinction between cosmology, which is the study of the large-scale structures of the universe, and cosmogony, which is how it all began. So the Big Bang is not really a theory of cosmogony. The Big Bang is a theory of cosmology. And the Big Bang theorists will firmly acknowledge that they cannot tell you what happened at the moment of creation. They call this the singularity, right? And they don't know what's going on there. Even Stephen Hawking, who's one of the great scientists of our day, he made it his life mission to try to mathematically describe this thing, and he couldn't do it. He failed. He discovered a lot of other cool stuff in the interim, but he didn't achieve what he wanted to. Anyway, I think we all know this story. I do want to read to you, if I may, one passage from this section of the Bhagavatam. So after the incarnation of the first Purusha, the Karanavashe Vishnu, the Mahatattva, or the principles of material creation, take place, and then time is manifest, and in course of time, the three qualities appear. Nature means the three qualitative appearances, talking about the modes of nature. They transform into activity. So here's the hypothesis that I want to put out there, is that what scientists describe as the Mahatattva, which is the bulk material energy, not manifested into any individual or unique or discrete forms, but just the bulk material energy in and of itself. That is the singularity that the modern scientists are describing. And I'm going to develop that thought here in a moment over the next few minutes. So material activities are called by the Mahatattvas being agitated. And so when we talk about cosmogony, we hear about branes, B-R-A-N-E-S, vibrating together, and then quantum entanglement just happening through the agitation or the interlapping of these underlying subtle fields. At first, there's a transformation of the modes of goodness and passion, and later, due to the mode of ignorance, matter, its knowledge, and different activities of material knowledge come into play. The self-centered materialistic ego, thus being transformed into three features, becomes known as goodness, passion, and ignorance in three divisions: the powers that evolve matter, knowledge of material creations, and the intelligence that guides such material activities. So within here, there's matter, but there's also consciousness, and there's knowledge of matter. So here, Brahma is telling Narada that, as we've heard in some of our discussions, consciousness is not a concomitant effect of the universe. It is a fundamental ingredient of the universe. Narada, you were quite competent to understand this. So here, this is what I want to get into right now. So from the darkness of false ego, the first of the 5 elements, namely sky, is generated. Its subtle form is the quality of sound, exactly as the seer is in relationship with the seen. So here what Brahma is saying is that the first material element that's formed is what Prabhupada translates here as sky. He translates it in other places as ether, and this is the Sanskrit word akash, which means space also. So this is repeating actually exactly what the material scientists say, which is that the first thing into this universe that was created was the space that the universe is within. So space rapidly expanded. The Bhagavatam is actually in full agreement with the modern scientists on this point. Its subtle form is the quality of sound, exactly as the seer is in relationship with the scene. So we saw that the scientists will say that it was electromagnetic vibrations that filled the early universe. The Vedic version is that these vibrations were actually sound vibrations. And I think that can raise some questions as to what is really the nature of sound. But we continue. Because the sky is transformed, air is generated with the quality of touch. So we know from the Big Bang that as space rapidly expanded, it cooled and condensed into mass-bearing matter. So the property of something that has mass is that I can touch it, right? I can't touch light, but I can touch this table because this table is bearing mass. And so again, we see that the Bhagavatam is in broad agreement with what the material scientists say. As matter forms, or as this universe forms, it manifested from a subtle state of space to a slightly more tangible state of air, what is called air here, in which I will draw the analogy of baryonic matter, mass-bearing matter. Similar to the previous succession, the air is also full of sound and the basic principles of life: sense perception, mental power, and bodily strength. So along with mass-bearing matter came the ability to perceive mass-bearing matter, the senses, mental power, and bodily strength. When the air is transformed in course of time, in nature's course, and preview, we'll talk about time next week, in nature's course, fire is generated. So we know also from the Big Bang Theory that once mass-bearing matter was formed, under the force of gravity, it was able to fuse together to ignite stellar fusion. And what is a star but fire? And so in course of time, in nature's course, fire is generated, taking shape with the sense of touch and sound. Since fire is also transformed, there is a manifestation of water full of juice and taste. As previously, it also had form and touch and is also full of sound. And water being transformed from all variegatedness on earth, and water being transformed forms all variegatedness on earth, appearing odorous, full of juice, touch, sound, form, respectively. So we see here in the Bhagavatam, it's describing a process of creation that goes from subtle to gross. And this is actually the exact same thing that the Big Bang Theory explains. So out of interstellar nuclear fusion, we get heavier and heavier elements up to oxygen, for example. If you take the original hydrogen, mix it with oxygen, you get water. And then it even formed heavier and heavier elements beyond oxygen until we get terrestrial elements like we see on this earth, which is also the last step as described by the Bhagavatam. So in conclusion, I think the second canto of the Bhagavatam explains the process of creation pretty much in exactly the same way that the modern scientists do, as a manifestation of subtle elements to gross elements. The Bhagavatam has a couple additional elements in it that I think are noteworthy for future investigation. The first and foremost one is that the Bhagavatam explains that consciousness, and I didn't read the whole Bhagavatam passage here because I realized the clock is ticking. I encourage you to do this. This is the second canto, chapter 5. This is explained in quite some depth. Brahma goes on to explain that the senses themselves are formed out of these transformations: eyes, ears, nose, touch. So consciousness is a fundamental ingredient of the material world. It's not an effect of the material world. That's the main thing. The Big Bang, the Bhagavatam, yeah, I think that point cannot be emphasized enough. That here we see that the life is coming from the life. The life is not an effect of just the material ingredients. But there are also some open questions about the Big Bang Theory itself. For example, Still, nobody can describe the singularity. We can describe the singularity. We call it the Mahatattva. Alternatively, there's a pre-existing state of the Mahatattva called the Pradhan, which is undifferentiated, unmanifested material energy. The Mahatattva is the sum total of all of that energy, and the Pradhana is its unmanifest state. I think a lot of these questions are being called into question with the results of the James Webb Telescope. But another one is that scientists don't really understand why there were excess protons after the recombination, which allowed us to live in a world of matter rather than antimatter. And what would the difference be if we were all anti-material rather than material? And then finally, in order for this whole model that they've made to work, they do need to monkey with some of the evidence a little bit. So we see that the things that are furthest away from us in space are also the things that are receding from us the fastest. And that calls into question. So there's some force in this universe that is acting against gravity to push galaxies further and further apart from each other at the boundaries of the universe. Scientists call this dark matter or dark energy because they can't see it. But they can detect its signature in different places, but it's not visible. But what is the nature of this matter? And most of the universe is made out of this stuff, and we don't really understand it that well. And so I think the Big Bang, in conclusion, I will say the following things. Number one is there is no real contradiction between the process of creation as described by the Srimad Bhagavatam and the process of creation described by the Big Bang. And I think that anybody that's trying to make a distinction on the fundamental process is not that literate in one or the other. They just don't know what these things say. The other point that I want to make is that I think the Big Bang Theory is an excellent example of a scientific theory that does provide consistent, meaningful explanations for divergent phenomenon that we see in the universe that at the same time does allow itself to revision when new evidence becomes available. So we do see that the James Webb Telescope is calling into question a lot of this theory. And that is not an instance of scientists being dogmatic and being like, no, this is what the theory is. That is an instance of science progressing further as a feature of the science, not as a defect of the science. That scientific knowledge can be updated and should be updated as new evidence becomes available. So all of this stuff from the James Webb Telescope is really too new to comment conclusively on what it means, other than that it is calling into question some of this stuff. And we see the scientific community responding to this not in a dogmatic way, but in a way that fosters further investigation. And so I think in addition to it being necessary to understand the details of this theory, if we want to preach to people about what the Bhagavatam can offer in addition to it, I think it is also an excellent example of how scientific theories work in the real world. And so on that note, I think I'll stop. Sorry, I don't know. I apologize.
Wow, thank you so much.
Yeah.
Can you stop the sharing, please? That was excellent. Thank you very much. I really appreciate this. I just have one, something I didn't understand, I didn't grasp when you said it. So this new telescope shows that the galaxies are further away. Or that the redshift is greater.
Yeah, when we look into space, we see not only distance, but we're also seeing back in time. So they're existing at a point in time where we had previously thought that there could not be mature galaxies like that.
So
like
the
mature
fact that
galaxies
the redshift is greater, does that imply that the universe is older?
That in and of itself, it's not that the redshift is greater, it's that the redshift would put it at a point in time where previously it was believed that there wouldn't be any light in the universe. But now that there's huge galaxies. So previously we couldn't perceive light in that area, and so our theory matched that data. And we had good reasons to believe why there wasn't any light there. We can explain why things wouldn't shine. I gave you two of the reasons. One, there was no ionized atoms in the universe, which is what gives off light. And number two, whatever ionized atoms there were, the energy density of the universe was so great that they would immediately be absorbed and wouldn't shine. But then they found these, not just a star, but they found these huge galaxies shining in that area where they previously thought the universe was dark. And so they need that disrupts their explanation and causes the need for new explanation.
Okay.
Yeah.
All right. Yeah. It's
Which are not forthcoming. I mean, that picture was literally taken weeks ago.
Yeah.
It was released to the public.
I just saw it posted somewhere. Okay.
Yeah, in fact, I had to rush to get it in here because I thought I can't do this presentation without mentioning this, but I don't even understand it that well myself, other than what I just told you, because nobody does.
I really appreciated the reconciling of scientific method and this theory, and then what we are reading, so that there's no, always trying to be in an antagonistic relationship with the scientists, but it's part of we can incorporate what's happening as it's changing, and also incorporate what we understand from the Bhagavatam as that also changes. We kind of get new information. Our understanding is also expanding in it.
Our understanding. Well, your comment just reminds me of this famous letter that Srila Prabhupada wrote to. Can't quite remember where he talks about. This is in our BI archives, and I've often read this letter at the beginning of BI conferences. That Prabhupada talks about preaching to academics and learned people and scientists, and he says that they may be a little puffed up, and he says that's okay, they've earned it. And so scientists really want to be right. That's they want to know things and they really want to be right. And I think that the Big Bang is also an example of where they are actually right about a lot of things. And so we can acknowledge that, and we can also say, but here are some holes that are in here, and look, we have something that can fill that hole. Have you considered this, rather than an attitude or an MO, a modus operandi of just smashing, kick them in the face with boots. We all love kicking them in the face with boots, but has that been that is Prabhupada's mood of preaching, but we also know from Prabhupada's example that he adapted things to time, place, and circumstance. And so there's a time for, clobbering people over the head with the Bhagavatam. But there's also a time for having nuanced discussions.
Sure.
And in that letter, Prabhupada also mentions that Lord Chaitanya sat and listened to, I can't remember if he said it was Sarvabhauma Bhattacharya or Prakashananda Saraswati, but one of these people preaching nonsense to him. I think it was Prakashananda Saraswati. He sat and listened to him for days on end and didn't say anything. And just listened to him. And it didn't have this mood of, and then he was done and he said then he reflectively listened. He showed the assembled Mayavadi sannyasis that he understood perfectly well what they were saying. And then he offered his own evidence. But he didn't just become argumentative. He sat and he listened patiently for days. And Prabhupada said, even though they were speaking so much nonsense.
Yeah.
So.
Well, thank you. Stita D had mentioned here, well, there's a couple of things here. But curiously, the Catholic Church tends to feel that the Big Bang Theory supports the theological take of creation, or their theological take. That was more at the beginning.
Well, yeah. Sure. I mean, Lamada was a Catholic. I mean, yeah. The Catholic Church is not in the 15th century anymore in regards to its attitudes towards science. Maybe in regards to its attitude towards some other things, but in its attitude to science, actually, the Catholic Church funds and supports some of the world's most prestigious universities in scientific research all over the world. So that doesn't surprise me at all. Yeah.
Thank you. Okay, so any comments, concerns, questions?
Yeah.
Small part. Yeah, go ahead.
Yeah, that was very nice. Learned a few things. We had a cosmogony philosophy meeting the other day.
Yeah.
That was really special.
Yeah.
We had a few astronomers and Kandadi and Rita and Anuraj. And one of the issues that came up, a little peripheral what you're talking about, but I believe relevant and quite important, was the size of the universe.
Yeah.
And because we can read in the Bhagavatam certain descriptions, and there's even a description, is there one sun or multiple suns? These things come up. And so we took a few of these verses and analyzed it in detail. And what comes out is remarkably interesting. because what comes out is you can't go by the English. The English words are of universe. Sometimes Jagat is used, which might be universe, but it can also refer to solar system, refer to even the planet. We say Jagat Guru, we really don't mean the whole universe. We mean here. There's so the confusion comes from the lack of Sanskrit, because Prabhupada, by his own admission, I mean, by our own analysis, he's presenting philosophically as perfect as can be. By Prabhupada's own admission, the astronomical discussions, he said, frankly, it's not my field.
Well, I mean, I think that is a typical comment made by Sanskrit elitists, because it's not that the people who understand the Sanskrit understand it either.
Well,
So it's not, there are some language issues, and I know that my Guru Maharaj told me the other day that he's going to come and speak at our next cosmology conference, and he was asking me for, what should he talk about? And I think he should talk about these language issues.
Exactly.
But so there are, I don't want to divert too much from the Big Bang though, for now in this discussion.
Okay.
Yeah, I think you're right. I think just to say it's a matter of English versus Sanskrit is also a misnomer. Even within the Sanskrit, there's so much that we don't know.
Yesterday, Steve D. Mooney presented on Vamsidhar.
Yeah,
which is more or less contemporary of ours, and 100 years or 150 years.
No, but I think BT, sorry to interrupt, but I think in this particular point, I'm actually pointing to a case where there is no real disagreement between what the Bhagavatam is saying and what the modern scientific paradigm is. Unlike where, for example, I mean, I'm drawing from the second canto here, the fifth canto, it gives those dimensions of 4 billion miles or whatever, and that has nothing to, in my opinion, that has nothing to do with
I think
the modern perspective of the universe. That is a question for philosophers and Sanskritists.
And you're right, the answers aren't fully known, maybe, and even partially known, but there are enough answers there that when we dig into it, we don't lose our faith in the Bhagavatam, we actually increase our faith, is the point I was trying to make. As far as the Big Bang, there was an amazing quote by Carl Sagan in his Cosmos book. And when I read it a long time ago, the quote kind of shocked me. And he said this, he said, of all the ancient cosmologies and mythologies, the only one that comes closest to modern science is the Vedic version, because they talk about billions of years, and originally others talked about millions, or some conservative Christian thousands, but he said they even came up with 4.5 billion years for the Earth, which is amazing. But what I found surprising is he said the Bhagavatam is coming close to modern astronomy. Maybe a better way to put it is modern astronomy is coming close to the Bhagavatam.
I think the whole framing of that argument or the conversation is exactly what we're trying to get away from.
Tell me about that.
Yeah, why do we need to set these two things at odds with each other? They're different types of knowledge. Why do we think that there should be a reconciliation?
But there's some correlation.
So, but here, I mean, like this thing with the 4 billion miles roughly approximating the mean geocentric orbit of Uranus around Earth is an interesting correlation, but from a scientific perspective, actually it has no meaning. There's no causation behind a correlation like that. So, but here's the thing with the conversation about the distances in the Bhagavatam versus the distances in the material world. And this is why I went into this slideshow, and I go into greater detail of this when I do this with the middle school kids, because I think it's really important for them to understand the nature of the evidence. But for us, this is what we're talking against. We can't just say, no, the scientists are all wrong and the Bhagavatam is right, without addressing how is this wrong? How does this parallax not work?
It does.
Where does it fall apart? And so with parallax, and that's what the purpose of this is, with parallax using modern space-based methods, satellites, not stuff that has atmospheric interference or ground vibrations or whatever, we can see parallax out to millions of light years. And so if you're going to say that that's wrong, somebody needs to explain how this doesn't work. And this is millions of light years, and that's very difficult to do. It gets a little bit more speculative when we go further down the list here. So once we get out of the range of accurate parallax, we start using special types of stars and supernovae. And because we can see the spectrum of the star and we can detect the mass of the star by gravity, we can estimate how bright the star should be. If we know how big it is and we know what it's burning based on its light signature, we can estimate what is the absolute magnitude of this thing, and then of the star, and then we can see how bright is it really, its apparent magnitude. And by comparing its apparent magnitude with our estimation of its absolute magnitude, we can estimate how far away it is from us. And using these methods, we can get out over 100 million light years from us. A light year is trillions of kilometers, not 4 billion miles, trillions of kilometers. And we're talking now about hundreds of millions of light years. But these methods, granted, these are a little bit more speculative. And then as you get further away, you start using redshift, and you can only accurately measure the redshift of certain types of objects. So it's not like we see the redshift everywhere. The further away from you get to the Earth, the more speculative these distances mean. But even parallax, which I find is something that is very difficult to argue against, is showing the universe to be way bigger than the dimensions in the Bhagavatam. And so if that is the route that we want to go of trying to recognize these things, I feel like you're going to have a problem.
I suspect we get back to the second canto. Lord Vishnu is taking his nap and breathing, and millions of universes come out. So when millions of universes come out, that implies an expansiveness way beyond dimensions that may be given of a particular locality in the fifth canto. And that's how I understand it.
Absolutely. And I think, and science is moving in this direction. And even these latest pictures from the James Webb raise the question of, did they accidentally point this camera through a black hole? And are we actually accidentally seeing into another universe?
It's very
in fact,
possible.
or, there's the idea that, we're expanding in this direction, but there was an expansion and a contraction in the other direction too, which is very much in line with the Bhagavatam. So I think I think it's important to recognize that qualitatively, actually, what the Bhagavatam describes is the same as.
I like that.
The scientists have more quantitative detail, which is valuable, I think, for creating a clear picture of the universe. And this is where Lemaitre was coming from, and people that preceded him also. I think where modern quote unquote modern science has gotten off the track, and what Prabhupada was really speaking against beyond the details of the theory, is that what are the scientists doing with the knowledge? We've developed quantitative knowledge of the universe with a mindset of wanting to exploit it, and no longer a mindset of wanting to understand Krishna's glories, which is what Kim Pritchett was asking Sukadev about. So the knowledge is the same. And Prabhupada also writes in the introduction to the Bhagavad Gita that the activities of a materialistic person and the activities of a devotee may appear to be the same. It's their consciousness that is different.
And the second canto also goes into the modes of nature as a factor.
Yes. The fifth. So I think also related to the language issue, the fifth canto is, unique in many ways in the Bhagavatam. We've discussed how the prose in the fifth canto is unique. I think the fifth canto is also unique in the Bhagavatam, in that it draws more directly and more heavily from other Puranic literature.
I think so.
Whereas, for example, our ninth canto has the story of Ramachandra, or there's a whole Purana about the Matsya avatar. There's a whole Kurma Purana. We just have a little bit of that in the language of the Bhagavatam, but the fifth canto appears to be taken like large portions of the Vishnu Purana have been put into the fifth canto.
I call it the speed bump on the way to the 10th canto. slow down, think about it.
Right, any questions online here? Small question. Is there a word for this sort of reverse engineering of starting from the Bhagavatam makes sense of certain? Yeah, it's called mental speculation. No, I don't know. This you weren't with us on our I think one of our previous talks. But a lot of this whole seminar arises out of the idea that when there is information in our religious scriptures that contradicts our scientific knowledge, that can be a cause of losing faith in our scriptures. And how do we as devotees or spiritualists try to reconcile that? And so that's what the whole exercise is, really. And I'm just number one, presenting the science as it is, because I think in the past, the devotional community hasn't been terribly literate with these things. And then I'm also presenting ways in which it can be understood without really advocating for my own beliefs, but rather advocating for a pluralism of viewpoints, of really being able to see things from all angles of vision without there really having to be a right answer other than we should all just chant Hare Krishna and take prasad.
Well said.
Yeah. Any other
It
questions?
also doesn't bring you into a kind of weird relationship with the thing like you started off saying that we use with for almost everything. So how can you take an kind of an antagonistic, perspective with science when it's really part of my life?
Yeah, and
then
that's
it becomes unhealthy.
Yeah, and that's one of the reasons why I did the whole flat Earth thing. Also, it's not because we need to debunk the flat Earthers, but there's like a social aspect to the amount of cognitive dissonance that goes into that. Like how like mentally schizophrenic people need to make themselves to out of hand reject thousands of years of science and at the same time be fully dependent on the creations of that paradigm in terms of their GPS, whatever it is they're using, electronics, all of it.
Steve D has his hand up.
Stita, I'm so used to you just barging in and interrupting that I didn't.
Can you hear me?
Yeah, go ahead.
All right. I'm trying to behave myself. I found out where to.
You're doing an excellent job. Too good, I would say.
I can lower it now too. Look at that.
Oh my God.
One thing is just semantically, it's science is falsifiable, so it's never actually right about anything.
Right.
No, that's not right. It's falsifiable. No, I'm just teasing.
Correct.
Yeah, so I think sometimes if we talk about science, if we use language like according to current scientific consensus or scientific perceptions, and then there's a perception in the Bhagavatam, and then there's two ways of looking at this thing. Not that the scientific perspective is Maya, but it's a different mode of analysis, and perhaps there's areas of correspondence between these apparent modes of perception, because we're saying like in the fifth canto, apparently you can perceive it, or at least people are claiming they can perceive it. I don't know, but if we use that kind of language, sometimes you could sort of tone down the some of the emotions that people from a scientific side and maybe from a Puranica side sometimes invest in these things. I don't know. Utility is the principle. But they do seem to be perceiving something. Then the other thing is, the Catholic Church is very inclined to the Big Bang Theory, not because it's science per se, but because it conforms well with their understanding of creation, that God creates from nothing.
Yeah.
And that was the initial analysis. Of course, now I'm trying to get this Scientific America cover attached here, but I can't figure that out yet. But there's mathematically considering that maybe the Big Bang's a blowout reflection of some alternate higher dimensional something or other, which now sounds more like Plato, or maybe the Bhagavatam. So there's all kinds of things going on there. But the Catholic Church isn't inclined towards the Big Bang because they're in the 21st century. But if they were in the 15th century, they still would be inclined, because it seems to fit well with their theological arguments.
Fair enough. Thanks.
I have a question about going back to the creation. Is there anything in anything observable that could perhaps point to the differentiation of the gunas at that point, from the scientific perspective?
Well, I think that is the question. And I think that, I mean, I was thinking about that actually, it was just when I was preparing the updates on this morning, is that, you know, what do we do with this information, or what can devotees who are interested in pursuing this topic further do with this information? And I think that is the question. So when we hear about the gunas in the material world, we tend to think of the action of the gunas: goodness, passion, and ignorance is maintenance, creation, and destruction. And so obviously we observe these things going on, but what is the fabric of the gunas?
Right, because they're mentioned in that second canto that at some point here they come.
Yeah, and it actually goes into a lot more detail than what I explained, like how the mind corresponds with what. But and here's a language issue: is that the translation is a little bit difficult to follow.
What chapter is in the
It's
second canto?
the 5th chapter.
2-5.
And then Kapila Dev gets into it again in the 3rd canto, which we'll get into not next week, but in a couple of weeks. Next week, we're going to talk about time. And to get back to BT's point about Carl Sagan, so actually, anytime the modern scientists revise the age of the universe, it gets older and older and older. So Alfred Kelvin, when they first started thinking the Earth is older than what the young Earth Christians were saying it was, he thought the Earth might be a few million years old. And then they were like, no, actually it's billions with a B years old. The lifespan of Lord Brahma is 311 trillion years. And so we, first of all, have no means of detecting time on that scale. Really, the oldest that we can date things on Earth is at the age of the Earth. So the isotope, I'll get into more detail about this next week, but this is only to say that I think that the way that we are able to date things absolutely using radiometrics and whatnot is limited by our understanding of the Higgs boson and the particle that imbues matter with mass, or that makes mass baryonic matter. And that is to say, because when we measure things radiometrically, we're using a mass spectrometer. We're measuring the ratios of the masses of isotopes to each other. But we don't really understand that well what gives matter mass. That's why they called the Higgs boson the quote unquote God particle. And that's why they call the Higgs boson the quote unquote God particle, and they claim to have found it. And there's a whole documentary about how they found it, but I have my doubts about if that is really what they found. They did find a new subatomic particle, but they did not find it at either of the energy levels that Higgs predicted it at. So why do they, so this also gets into some of the nature of, like, who decides when the scientists are right, or if they just needed a media blitz. But I don't know. Here we got the black hole at the beginning of time, but time can also go in the other way. And so there would be a whole other universe expanding out, going in the backwards direction of time. And then if that universe plays their time forward, they'll get back to the same black hole. And that is definitely what
the subtitle there is, do we live in a holographic mirage of another dimension?
The Matrix.
So it's going beyond the beginning of time.
Yeah.
But
that is also, yes, we definitely do. Yeah, that's what Om Purnama Da Purnamidam means.
So
if you take any slice of Krishna, all of Krishna will be in there.
So there could be
if you remove anything from Krishna, the thing that you removed has all of Krishna in it, and what is left behind is still all of Krishna. And that is exactly how a holograph works. So there's some
intriguing correspondence there, and it's interesting. But as with Lemaitre was a Catholic priest, he was a Jesuit.
Yeah.
And the Pope got all excited when theories first came out, and the Pope Paul, I guess he was all excited. Oh, this is so exciting. It proves stuff. And Lemaitre came back. No, it doesn't prove anything. That's not science. It could be interesting, but we can't say that as a scientific principle. So similarly with this Scientific American cover, which
Hubble was like right on his heels.
But this is Lemaitre's correspondence with John Paul. That we're not going to say science proves Catholic theology because of the issues that we've already raised and others have raised as well. We're going to discuss, as a scientist, is going to discuss black hole in terms of scientific evidence. But here we have this black hole at the beginning of time as a potential, and they're doing high-end mathematical analysis of this, and there's professional papers on it far
Yeah.
beyond so it's interesting, and it's of course falsifiable if considered in a scientific perspective, but it's very intriguing how serious scientists are looking at this Big Bang as some sort of portal or an expression, a mirage, a reflection of another dimension, which they're not going to say is Vaikuntha Loka perhaps, but it sort of is intriguing from a Vaishnava perspective.
All right. Vega, you popped your camera and you want to say something? Nice to see you.
Yeah, hi.
Hi, Haribol. No, it's a fascinating subject, especially the science part is way over my head, but when you just mentioned the part about the holographic universe, and then it might come back the other way, it reminded me of that movie Groundhog Day. It's like, do we have to keep going through this same thing again?
Yeah, thanks for not mentioning the Matrix again. You got it covered. Yeah.
Yeah, that's
Groundhog Day. Yeah.
Yeah.
Haribol.
All right, so next week, time?
Next week we will discuss time, and we will look at the question: does modern science falsify the Vedic age of the universe?
Okay.
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 Thank
Thank
Stephen,
you very much. Thanks
the
for coming.
article. Very nice.
We look forward to seeing you again.
And also the article in Back to Godhead about the size and age of the universe. So all these things are, this is the latest one. All these things are nicely connected. And thank you very much for Charananda for your presentation.
Sure. You're welcome.
And thank you all for your attention and for your presence. We'll see you next week.
There are presents? I didn't get a present.
Your
Sorry.
presence is our present.
Yeah.
Yeah, see? That's it.
Oh,
That's
yeah.
the
Okay,
present.
that's true.
Okay.
Okay, thank you.